Now I'm going to teach you about the group O3, the group SU2, their relation to each other, and Euler angles. First, we will start off with the definition of a group. A group is a collection of elements This collection of elements must be closed under composition. It must follow the associative property. This group must include the identity, and it must have the inverse to every element, such that it times its inverse is equal to the identity. O3 is the group of all 3x3 matrices, which are orthogonal, where orthogonal is a property such that in R, some element in O3, R times its transpose is equal to the identity, and similarly R times R transpose is equal to the identity. We have that these elements in O3 are matrices, and these matrices act on vectors such that these vectors are in R3. We have that O3 is a length-preserving group. It's a length-preserving group, and we call length-preserving groups rotation groups. We call this one in particular, O3, the rotation group, because it acts on vectors in R3, and we live in R3, so we're a little bit biased in that. But we call this O3 the rotation group. And what it means to be length preserving is, so we define the length of some x to be x dot x, where that's equal to x transpose x. Now, if we act on these vectors, if we transform them with r, we get the square root of rx transpose rx. And then this equals x transpose rx. And since these elements are orthogonal, we have that xtx equals x dot x. I could also say at this point that it preserves length and that we use the property of orthogonality in order to prove this, and I'll leave that as an exercise to the listener. The next thing we have is that these elements in O3, all of them have a determinant of either plus or minus 1. This again depends on this orthogonality. I'll leave that one up to the reader this time. No, I won't. So we have that I equals RTR, and we have that the determinant of I equals 1. So we have that the determinant 1 equals the determinant of R transpose R is equal to the determinant by properties of the determinant R. And from linear algebra, we know that this is just determinant of R squared equals 1. Square root both sides, we could pick up the plus or minus sign, and we have that the determinant of R is equal to plus or minus 1. Now, that leaves us with two sub-collections of this group. I call them sub-collections because the collection in which the determinant of R is equal to minus 1, we notice that the determinant of the identity equals 1, and so this sub-collection does not include the identity, so it's not a group. However, the determinant, so not a group, so we don't, this one's not interesting to us because of this reason. However, the determinant of R such that it's equal to plus 1, it is a group. it's special to us, so special that we call it the group SO3, where this S is special. And all of these, and again, all of the elements in SO3 follow the determinant is equal to +1. And the identity is in this group. This group is also has a Lie algebra. But firstly, so SO3. So we have this SON structure groups. And this depends on n times n minus 1 over 2 parameters. So we know that SO3 depends on 3, 3, 2, 2, 3, 2's 3. 3 parameters. This is the rotation group, so we call these parameters theta 1, theta 2, and theta 3. Okay, so now also SO3 depends on these 3 parameters continuously. We can move from the identity to any value that these can obtain without jumping or skipping as if we would the determinant is equal to -1, for example. Because then from the identity to any piece, any element in this group would be discontinuous. So it depends on these 3 parameters continuously. So it is a Lie group. This Lie group is also a manifold, and this manifold looks like a sphere. This manifold looks like a sphere. And a sphere, in fact, of radius pi. And that's because these 3 parameters are defined on the interval minus pi to pi. Now, on this manifold, we have that antipodal points are identified as the same point. And that's because if you rotate an object by pi, you receive the same thing you would as if you rotated it by negative pi. You can see that clearly with your hand flipping, for example. A little bit hard with the hand, maybe a book would be better. Let's take a path from the origin and go out to this point pi. The points are the same point. Antipodal points are the same point. So then we appear on this negative pi. And let's go from this negative pi back in. This path is a closed path that cannot be shrunken down to a point. So this tells us that SO3 is not simply connected. We have that SO3 is not simply connected. And because of this property, because it's not simply connected, that means that there exists a larger group. There exists a larger group such that SO3 is a subset of this larger group. And it is simply connected. And it is simply connected. And the smallest group, which contains SO3 and is simply connected, is called the universal covering group. And the universal covering group for SO3 is SU2. A property of this universal covering group is such that the regular representations of SU2 are equal to the projective representations of SO3. What does that mean? Why is that helpful? So what I just said was that the regular representations of SU2 are equivalent to the projective, I'm going to call it PR, if you don't mind, projective representations of SO3. What does this mean? Why is this helpful? What is a projective representation? So let's look at quantum mechanics for a moment. In quantum mechanics, we have states. We have state psi. And if we want to take the expectation value of momentum, say, in some state psi, then what we do is we take this and we take this inner product like this to find the expectation value. Well, this results us in the same thing as if we were to have the state e to the I theta phi, because we would have this. And these guys subtract from each other and equal 1, and we're left with these two being equivalent statements. So what that means is that all of these e to the I theta psi's get mapped to some psi. And this is a projective space. And because we have a projective space, we need projective representations in that space. So what that means is when we have, so now we have projective representations. So what that means is when we have some representation of a group, call the representation U of a group element R1 times U of a group element R2. Projective representation is such that this equals some phase factor where theta depends on R1 and R2 times U of R1, R2. And it's these, and it's this prefactor, this exponential term that's difficult to deal with. We don't know how to find what theta, how it depends on R1 and R2. It's difficult. It's nasty. So in quantum mechanics, instead of working with these projective representations, it's nice that SO3 is not simply connected, because that means it has a universal covering group, which is the smallest group, which contains SO3 and is simply connected. That is SU2. And SU2, the regular representations of SU2 are equivalent to these projective representations of SO3. So this is nice. This is a relation. And now I'm going to talk about SU2 as a group. SU2 is the group of special unitary 2x2 matrices. Where special we discussed earlier, the determinant of some, let's let B be in SU2 so we don't get B and R confused. So the determinant of B is equal to 1. Unitary is similar to orthogonal. Unitary is that B times dagger, where dagger is the transpose conjugate. B dagger B is equal to the identity is equal to B dagger. So transpose conjugate, whereas before we just had the transpose and we didn't, and so this is the transpose conjugate. Before we were working in R3, so we couldn't have a conjugate, but here these B's act on a vector such that this vector is in the complex plane, C2. This one also is length preserving, and this is quantum mechanics, so this is helpful in quantum mechanics because we have that, that lengths are probabilities. Probabilities are lengths in quantum mechanics, and so when we're working with these groups, we have that probability is conserved. So that's a nice property. SU2, as the SUN structure depends on n squared minus 1 parameters. So we have that SU2 depends on 2, 4, 3 parameters. And interesting side note, SU2 is the symmetry group for the weak force. It's a symmetry group for the weak force. And these parameters turn out to be W plus, W minus, and Z, the gauge bosons for the weak force. And SU2 depends on these three parameters continuously. Also, SU2 is also a Lie group, and it also has Lie algebra. A Lie algebra is the tangent plane at the identity of the manifold. And since SU2 and SO3 are, I believe, isomorphic at the identity, let me check my wording here. This is important. Isomorphic at the identity, yes. So 1 to 1 and on 2, so they can be mapped at the identity. And the Lie algebra is a tangent plane at the identity of a manifold. So SU2 and SO3 share the same Lie algebra. And we don't know what groups, we don't know what elements in these groups look like. And so we utilize this Lie algebra to help us, because the Lie algebra, we can take infinitesimal rotations about the identity, and then when we exponentiate them, we result with a group element. This is something Timonfeld discussed last week. I'm going to propose a little bit different of a definition, though, however, for them. I'm going to say that, so we have infinitesimal rotations. Let's take some infinitesimal rotation such that we have the identity plus some epsilon I j, where j is a generator of this rotation. J's can also be thought of as the basis vectors for the Lie algebra. So this gets us infinitesimally far away from the identity. So let's try to get further away from the identity. So what we do is, instead of this, we take it and we go in steps, in times. And then we take that limit as n goes into infinity, and we get somewhere. And then we notice that this is equal to the definition of the exponential e to I theta j. Theta now, because epsilon was some infinitesimal, now we've gone some finite distance theta. And now this is an element in our Lie group. Each rotation R that we make can be written as a multiplication of some rotations. I'll explain that in a minute. Let me write this down. So what it means is any R in SU2, let's call it B then, because we were dealing with B earlier for SU2. So any B in SU2 can be written as e to the alpha j3 times e to the beta j2 times e to the gamma j3. That might be backwards, and multiplication is not commutative here, so this matters also. Take a second and read. Alpha, beta, gamma, yes. Okay, so these J's are the generators again, and our generators do not commute. We actually have that Ji, Jj is equal to epsilon I jk, jk. Does not commute. So that means that this does not equal to e to the alpha j3, oh dear, j3, plus beta j2 plus gamma j3. Does not equal that, because addition is always associative, and this would reflect that we lose the information that these can't multiply. So we're not allowed to do this. this can't happen. We have to deal with this. What these alpha, beta, and gamma are is these alpha, beta, and gamma, I guess I'm writing it backwards, gamma, beta, and alpha are Euler angles. And they look like the following. So we take this sphere, and it's a little bit easier if I do this one way rather than the other way. Okay, so I'm just splitting the sphere in halves. I hope that this is legible, and I hope that what the following is makes sense to you. So we start with an axis right in the middle, and we start off with a typical z, x, y. First, we rotate about the z-axis, so such that z equals z prime, and we see that x and y lie in this plane right here. So x and y are just going to follow this line. They're going to curve on this because we're just rotating around the z-axis. So our x is going to go somewhere here, say. Our y is going to go somewhere here, say. X prime and y prime, where we just did the, I believe, the alpha. Now we're going to rotate about y prime. So that means that this axis is going to be saved, so y double prime stays the same. And now we notice that z prime and x prime lie on this plane. So we're just keeping about this. This is staying, and our z prime and x prime are going to rotate down a little bit. Okay, such that, call this x double prime, call this z double prime, where now we've made some beta. And y prime equals y double prime. So now we're dealing with these double primes, so here, here, and here. Now we're going to make one last one. I need to make a new line for this. I don't want to confuse you in the beginning with it. But it's right like that. And something we're going to notice here now is that, again, this y double prime and this x double prime lie on this line. And now we're going to take z double prime equal to z triple prime, going to rotate about this z-axis, and this x double prime and this y double prime are going to rotate up the plane, such that it comes, I'm only going to rotate it a little bit, just so we don't get confused in this area. And y triple prime. So this last one was gamma. This last one was gamma. So now I'm going to highlight our ending spot. And the thing that we learned here was that with these three rotations, we can compose any other rotation with these three rotations. And we call them Euler angles, and our group elements can be represented as multiplications of these guys. And last note is that because this doesn't commute, we want a way to do multiple rotations. Is that how I want to say that? I don't think so. But I'm not sure of a better way, so I'm just going to keep going with it. So we want to be able to do a lot of these rotations. We want to compose one rotation with other rotations. So how we do this is we take e to the, to the h, j1, j2, where this h, this component is called the Campbell-Baker-Hausdorff theorem? Baker-Campbell. Baker-Campbell-Hausdorff theorem, such that h of j1, j2 is equal to j1 plus j2 plus 1/2 commutator j1 with j2 plus 1/12 commutator j1 with commutator j1, j2, plus, etc. Dot, 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 dot. And it's actually an infinite sum of nested commutators. Not actually sure how that's computed. But that's how we find them. And we know that, and last note is that we know that this e to the h, j1, j2 is an element of SO3 still, because we have that this commutator is an element of SO3. And so we can just split all these e's up and see that each of them is a component. And that concludes my discussion. Oh, you couldn't see that at the end. We just had that e was in this group also. Well, that concludes my discussion. I hope you learned something, and I hope I didn't fuck up too much. And my fact for you is that there exists black holes which are the size of our solar system. I think that's pretty fantastic.